share my screen through my iPad? Would that be okay?
Yeah, I think you can share.
Okay, great. Thanks.
Ma'am, could you please kindly introduce Dr. Anshu again?
Again,
Yeah.
okay. Sorry. Uh, so now our next speaker is Dr. Anurag Anshu, Assistant Professor of Computer Science at Harvard University. His interests are in quantum complexity theory, quantum many-body systems, quantum Shannon theory, and quantum learning theory. The title of his talk is NLTS Hamiltonians from Good Quantum Codes. So over to you, Dr. Anurag.
Thank you so much for the kind introduction, and thanks so much for the invitation. It would have been wonderful to be there in person, but this is as good. So I thought I would make this presentation in an editable form so that, if the questions come, we can jump right ahead and start doing our calculations. And, please, sorry for being late, and please do interrupt me anytime for questions, throw oranges or whatever feels appropriate if things go wrong.
So
all right.
Better we can take questions in the last 10 minutes.
Oh, I see. That's fine. Anything is fine with me.
Okay.
Interruptions are totally fine as well.
Okay.
Great. Thanks so much. All right. So this is a joint work with Nicholas Brookman at U Bristol and Chinmay Nirkhe at IBM. Here's the archive link for it, or the number for it. So this talk consists of a collection of topics which include quantum complexity theory, local Hamiltonians from physics, and also quantum error correction. So I thought I would spend roughly 5 minutes or so introducing these basic concepts, or catching you up with it. You might most likely be familiar with these. So I'll just spend 2 slides, just on the introduction, and then get to the main ideas. So let's talk about the notion of model of computation. When we think about computation, let's say model of quantum computation, usually what comes to our mind is the circuit model, that you start with a collection of qubits, which are in certain state 0, for instance, in the beginning. They're all in this set to be in state 0. And then a whole collection of gates act on it step by step, layer by layer. At the end of the computation, we measure a certain fixed qubit, and the outcome of the measurement is the answer to the computation. And we hope that this computation correctly solves a problem, for example, factoring. Now, this is a usual model of computation that we think of. But there is another model of computation, which is something which is very hidden in one of the important results in quantum complexity theory from 1999 due to Kitaev. And in this model of computation, you don't initialize qubits in all zeros and set a collection of gates. You define a local Hamiltonian, which I will formally define very soon in a couple of slides. You imagine there's a collection of qubits arranged on a lattice, and you define a collection of interactions between them. So this qubit is interacting with this qubit in certain manner, and so on. That defines a local Hamiltonian. For instance, many people would be familiar with the Heisenberg model of Hamiltonian. That's an example. But in general, imagine you had the power to set up any interaction between qubits that you wanted. If you could do that, then it turns out that the ground energy of this local Hamiltonian also encodes the answer to the computation. So the way you do it is that to define this Hamiltonian, you look at this circuit, look at the gates, and the interactions would depend on the gates. And once this Hamiltonian was set up, if you were able to compute the ground energy of this Hamiltonian up to an error of roughly 1 over the number of particles, for some technical reasons we have not get into right now. If you do this, then you would be able to know the answer to this computation as it is. So this is known as the quantum Cook-Levin theorem, and it's a really deep connection between quantum computation and physics. In fact, After this work was written, this paper was written down. In fact, it was written in a book by Kitaev. After that, since then, the field of quantum complexity theory and many body physics have really gone along together for a very, very long time. And some very interesting results have come out of it. A very interesting conjecture that's wide open since 1999, probably, or 2001, in this whole domain is it enough? Is it possible to set up a Hamiltonian here for every quantum circuit in a manner that even if I were estimating my ground energy not so precisely, but rather coarsely, let's say I was estimating the ground energy up to error 0.001 times the number of particles. That's much larger than 1 over n cubed when n is large. Would this also suffice to get the answer to the computation? That's the heart of the quantum PCB conjecture, which I will not need in any form more than what I described here, and this will show up a couple of times in this talk, but not necessarily in any serious manner. So to understand the main results of this talk, you don't have to necessarily understand this conjecture. But this is something which is wide open, and I just put it out there as one motivation. All right. So any questions about this? Sorry, it's in the end. The questions are supposed to be in the end. All right. So another notion that I'll need is that of quantum error correction. So again, I'm going to very briefly touch upon it and get to more precise definitions later. But let me quickly recap the classical codes. A classical code is a collection of code words. So for instance, a repetition code is a good example where I put encode 0 into a long sequence of zeros and a 1 into a long sequence of ones. And if you look at the space of n-bit strings, if you just think of that space, which is also known as the Haber cube, the code words of a code are supposed to be far from each other in Hamming distance, so that if some error happens to it, the error does not take this code word too far. So you are still, even in presence of errors, you can tell whether this was the code word or this was the code word. So the classical codes are kept far away from each other, the code words, and this is known as the distance d. And in the classical error correction, people want a lot of nice things. So for instance, large distance helps to make sure that you're able to correct a lot of errors. Large rate means that you are able to encode lots and lots of bits into your code. So that means there are lots and lots of points that are far away from each other. And one nice property that people often want is local checks, which means that if I want to know whether a string was in the code space, it was a code word, then I just need to check a few bits for that, or close to the code space. So in the case of repetition code, for example, it's enough for me to check that these neighboring bits are equal. Although I have to go along and check all of them, but it's still desirable to be able to check few bits at once. So I'm able to check these 2 bits, and then later these 2 bits, and so on, and that makes sure that I'm in the repetition code if they're all equal. So this is what is something very standard in classical error correction, that people want large distance, good rate, and local check, which is also known as the low density parity check, or LDPC condition. All right. The quantum code is a generalization of classical code. A classical code corrects errors of the form where you suddenly flip a bit at random. In the quantum case, you can not only flip a bit, which is an X error, where you can also make a Z error, put a phase somewhere. In this case, we need to combine 2 classical codes in a clever way, and that's the CSS code. The local checks, also known as stabilizers, they have to be in both X basis and Z basis. X basis checks for Z errors and Z basis checks for X errors. So that's a very, very fast recap of quantum error correction. I'll again not need too much ideas than what is there in this slide. All right. So let me go ahead and jump right into the topic. So let's go back to this notion of local Hamiltonian that I introduced in the first slide. And let me define it formally, and then point to a very motivating question. So as mentioned, a local Hamiltonian on a collection of particles that you see here in red A local Hamiltonian is a way to describe the interaction between particles, assuming that the interaction is local. That means, for instance, these three particles are interacting just with each other, interacting locally. Similarly, these three particles are interacting locally, and so on. So the way we write down a Hamiltonian for this, we write down a matrix on the space of n qubits, which is a 2 to the n dimensional vector space. This Hamiltonian is a big matrix. It's a 2 to the n times 2 to the n dimensional matrix, as any matrix in a big vector space. But it has a special property that it's a sum of local terms. Each term hi, similar to Heisenberg interaction, each term hi just acts on a few qubits. So for instance, this hi might act as some operator on these 3 qubits followed by identity on everything else. So that's a local term. We'll assume for convenience that the local term, each local term, its energy is bounded. So which means that there's not too strong interaction somewhere in the system, and each term is positive. That is, the energy is non-negative and at most 1 for each term. Of course, when you add them up, the energy can scale a lot. I will also not assume that these particles are sitting on a 1D or 2D lattice, and we'll assume for our purpose that these particles can be present in a very strange manner in a high dimensional world. Now, one could argue whether this assumption is valid for our physical world, but it turns out people are able to engineer interactions, long-range interactions between qubits these days. So it may be physically reasonable, but at this stage, it's a theoretical concept that the particles are just present, and each qubit participates in a few interactions, and each interaction acts on a few qubits. So once I have defined a local Hamiltonian, it's a matrix, it's a Hermitian matrix. Every Hermitian matrix has eigenvalues and eigenvectors. So this one as well, if I plot the energy, there is the smallest energy out there, that's the ground energy, and the ground state lives here. And the max energy can be very high. It can be as high as the number of terms. It's max energy of the order of the number of terms. And there's some intermediate energies. So ground state is something which people study a lot, definitely in physics and also a lot in quantum computer science because of the connection that I mentioned earlier. But here we'll be interested in not just the ground state, but also all the states which lie above the ground state. In fact, we will ask all the states whose energy per particle or energy density is the ground energy plus some constant times the number of particles. So we'll think of all the states here as a approximation to the ground state. It's like epsilon approximation to the ground state. And we're interested in these things. And the question that we will ask is, are there simple low energy states? Are there simple states in this regime? This question is inspired by the quantum TCP conjecture that I mentioned in the first slide. So of course, the notion of simplicity depends on it's in the eye of the beholder. But let's explore one notion of simplicity which physicists often like a lot. I just want to highlight this to show that this is a very subtle question, more subtle than it might seem. So here's an example of a simple state. You might say, okay, if I can write down my quantum state as a tensor network of low bond dimension, then it's a simple quantum state. But it turns out that it's not simple enough because tensor networks cannot be used to compute expectation values beyond 1D. So one could even ask whether this is really a good enough notion of simplicity or not. But let's say it is. Let's say this is a good notion of simplicity. Then it turns out there is always a low energy state. That's the Gibbs state for any arbitrary choice of epsilon, your energy parameter, which exists in the low energy spectrum of the Hamiltonian. So if your notion of simplicity is tensor networks of low bond dimension, every Hamiltonian has a simple quantum state, the low energy region. So that's not simple enough for us because it's hard to motivate a tensor network from computational point of view. Our notion of simplicity will be even simpler and in fact much more practical, I guess. And this notion of simplicity is a class of quantum states that we will call states that can be prepared by constant depth quantum circuits. So in this picture, I have described an example of that. So think of all quantum states that can be prepared by starting with all 0 states and applying a collection of gates layer by layer. And let's say I was allowed to apply only a constant number of layers. In each layer, the gates cannot touch each other. They have to be acting on different qubits. But constant number of layers are allowed, or maybe a little bit more than a constant is also fine. These class of quantum states are simple in 2 ways. First way is that they're easy to describe, which means that I just have to list all the gates that are applied instead of the amplitudes of the quantum state. So this quantum state could be acting on n qubits. It could have 2 to the n amplitude. But I don't want to do that. I want to describe it efficiently. So I want to just write down the gates that are there. Because the depth is a constant, so I don't need to write down that many gates. That's great. And also, I'll soon talk about this. This class of quantum states, you can use them to compute any desirable local expectation values up to precisely without any error. So that kind of goes beyond the limitation of tensor network. The tensor networks are not able to compute expectation values. So we cannot use tensor networks to compute expectation values. So this class of quantum states are very nice because you can use them to compute expectation values. And this notion of simplicity leads to this conjecture that was posted by Friedman and Hastings from 2014. In fact, I'll soon point out this conjecture has a lot of interesting motivations. So Friedman and Hastings asked, is there a family of Hamiltonians and an absolute universal constant epsilon such that for all states with energy density at most epsilon times m, the quantum circuit that is required to prepare those quantum states has large depth. It cannot be constant depth. That means it does not satisfy the notion of simplicity as presented in this slide, which means that, so they require depth to be at least log n. So what you're asking is that, is there a family of local Hamiltonians which I can think of as hard local Hamiltonians? Because any approximation to the ground state is complex from the point of view of quantum state complexity. It's not a simple quantum state of this kind. So there are several motivations to it. One motivation is that, well, if your quantum state cannot be described by a shallow circuit like this one, you can think of this quantum state as harboring long-range entanglement. That means this qubit is entangled far away and so on. Any quantum state that is short-range entangled can be viewed in some sense as prepared by shallow circuits, constant depth quantum circuits. So this conjecture would say that basically is pointing out, is asking for a family of Hamiltonians which are entangled even at high energies or at high temperature, which the superconducting people in this audience might relate to, but it's not quite that, but it's sort of same motivation. Similarly, there is a wave of activity in the class of quantum algorithms known as the variational quantum algorithms, which try to approximate the ground energy using shallow circuits or constant depth circuits. This would also be a limitation on those, that these quantum algorithms cannot approach the low energy regime of a class of Hamiltonians. But the main motivation for Friedman and Hastings was actually the quantum PCB conjecture, which I did not describe fully. But these are all the other applications of this conjecture. So a quick word on why quantum circuit depth. I talked about how short circuits can be easy to describe. You just describe the gates. But also you can use them to compute expectation values. That's why they're so popular in the variational community, in the community of variational algorithms. And the reason is as follows, that if you have a shallow circuit, a quantum state generated by a shallow circuit, you can use it to compute the local expectation value of any local operator in a reasonable time. So for instance, here is a quantum state, and I want to compute the expectation value of an operator, let's say poly Z, on the first qubit. I claim that I just need a computational time of 2 to the 2 to the t to compute this. And the reason is that, well, I've looked at the light cone of this operator, which grows twice for each layer. And this light cone spans a collection of 2 to the t qubits only. So to compute the local expectation value, I can basically set all these gates to identity. I can ignore all these gates. Even then, it's enough for me to compute the expectation value. And if I have 2 to the t qubits, the time it takes is 2 to the t to do the computation, exponentially in the number of qubits. So if t is log n, 2 to the t is polynomial in n, so my computation can be pretty fast. So this is one of the reasons why often this class of circuits is interesting, and also the reason why this is an easy class of states. So in fact, I will not explain this point, but just a quick mentioning is that if NLTS is false, if this conjecture posted here was false, then this famous conjecture of quantum PCP would also be false. That's one thing. A quick remark is that shallow circuits are also very interesting from pure physics point of view, because circuit depth is often a proxy for adiabatic evolution. So if you're thinking of phases of matter where you want to connect one phase of matter with another phase of matter using a shallow circuit, using a short time evolution, often short time evolution can be thought of as shallow circuit for all practical purpose. And our proofs also apply to those. So here's the main result that we have. We pick up the recent breakthrough quantum codes due to Pantelleev and Kalachev. In particular, we pick up their simplification by Leverrier and Zemmour. So it's a family of quantum codes that were discovered very recently, and almost 30 years after the first quantum code was written down by Shor. These codes are good in all sense. First of all, they encode linear number of qubits. The distance is large, and all the quantum stabilizers have constant weight. They act on a constant number of qubits. So these codes, we take these codes and we show that the Hamiltonian that comes from these codes, which I'll write down in a moment, has this NLTS property, which resolves this conjecture of Hastings, Friedman and Hastings, which is that suppose I choose my epsilon that I displayed here, this epsilon that they asked, if I choose my epsilon to be the relative rate or the relative distance squared, which is a constant according to these results, then any state with energy density at most epsilon requires a circuit depth at least log the number of qubits. So although they asked for a circuit depth of log n, we can prove a much larger circuit depth, lower bound of log the number of qubits. So any quantum state in that regime requires at least log n depth circuit to prepare. So what's the Hamiltonian that I mentioned here? This Hamiltonian is basically a very natural Hamiltonian for quantum codes. That's the standard way how a quantum code can be viewed as a physical system. It seems that my iPad is lagging behind iPad is really lagging behind, sorry. Maybe I should be slow. Sorry, so I was just mentioning here in this picture that that this is about the conjecture of Friedman and Hastings. Let me quickly one sec. Let me go back and come back again. Let me start this thing. Sorry. This is on time, so let's go back to Jamboard. Okay. And this seems to be more on time. Good. All right. Sorry. So the Hamiltonian of the quantum code is simply the Hamiltonian that is described thus by the stabilizers, which is the sum of the x and z terms. Yeah, there we go. So the Hamiltonian consists of x part and z part, as you can see over here. One sec. Sorry. The x part here, which is the x stabilizers and the z stabilizers. So there's a very natural way to define the Hamiltonian from that. All right. So let me just point out the key steps that go into the proof. And I will expand upon these steps, some of them in the following slides. So just like I showed this picture earlier of a classical code, which consists of a collection of points in a n-dimensional hypercube, n-dimensional set of n-bit strings. Similarly, we can think of the X and the Z part of the quantum code as two classical codes, and they have their own structure. The main result that we show is that the structure of the approximate code words, that means the code words that approximately satisfy all the checks, not all the checks, is the following. In the X part, the code words are clustered, grouped together in this manner, but between the groups, there is a large distance. Similarly, in the Z part, the code words are grouped together, and between the groups, there is a large distance. This property is crucial for proving that log n circuit depth is required, and I will get to that in a few slides. But it itself is a separate theorem, a theorem in some sense, a classical theorem about these codes. The key message is that there is a notion called expansion, a notion which is very natural to these good quantum codes discovered by Panteleev, Kalachev, and by Leverrier and Zemmour. The expansion implies this property of clustering that you see here. So I'll give in the next slide. In the next few slides, I'll motivate this particular phenomena, which is the main result. And a quick remark, which for those who are already working in this area, but not necessarily for the purpose of this talk, is that we need high rate quantum codes for this result, which in fact is one of the two main points here. And after that, clustering plus the phenomena of quantum uncertainty principle, which we all know since the days of Heisenberg. But in fact, what we use is the entropic uncertainty principle discovered more recently, 30 years ago by Ofnik and by two people, sorry, I forgot the name. So clustering and uncertainty principle lead to circuit lower bound, building on what was discovered by an important work by Lair and Harrow. So the plan from now on in the next 15 minutes or so is as follows. I will explain this phenomena of clustering property from expansion, and I will give a quick idea of why clustering leads to circuit lower bound on the quantum state. So first remark is that expansion is necessary to have NLTS property. And this might come as a disappointment for most physicists, I feel, in this audience. Although it never works out that way when I mention it, people are not disappointed, but maybe you'll be disappointed. It turns out that this property of NLTS that we are looking for, this property cannot hold in any local Hamiltonian that exists naturally in the physical world. Which are the Hamiltonians that live on a, let's say, a 2D lattice or a 3D lattice, or even a 1D spin chain? Some people claim, I'm not an expert, that Hamiltonians living in a black hole or something are long range, so maybe that's fine. But we are in a much more reasonable part of the universe. So in that part of the universe, usually the Hamiltonians are this kind, and usually you don't see. So you have to engineer these Hamiltonians specifically. So if you are able to engineer long-range correlation, then you can generate these Hamiltonians. But these are still local Hamiltonians because the qubits have to live in high dimension space. So here's a proof that this property requires some sort of high dimensional graph. It cannot live in a low dimensional world. And the reason is expansion. So let me kind of get to that. So here's a proof that any Hamiltonian, any local Hamiltonian respecting the 2D lattice structure cannot be NLTS. And for this, I will imagine these red particles living on a 2D lattice, and let's say these are interacting through these 4x4 interaction. So each interaction acts on 4 qubits at once, as you see in this image. So there are overall 16 interactions here, one for each 4 neighboring qubits. But of course, these 2 qubits don't interact with these 2 qubits. So this Hamiltonian is on square lattice, and the claim is that I can prepare very easily a quantum state of epsilon energy density using a quantum circuit of depth 2 to the 1 over epsilon square. So here's what I'll do. I'll take my 2D lattice, and I will break it up into many, many small parts. Each part has side length 1 over epsilon. So I'll do that to the whole lattice, and I will ignore all the terms that were acting on the boundary, and I will solve for the small square separately. So if I solve for the small square separately, it's a 1 over epsilon times 1 over epsilon. Let me just write it down. This is 1 over epsilon. This is also 1 over epsilon. Each square is of size 1 over epsilon square, and I can explicitly diagonalize the Hamiltonian in time 2 to the 1 over epsilon square, and I can prepare that quantum state in 2 to the 1 over epsilon square depth. And I just put these together. I just write down my state is basically psi1 tensor psi2 all the way till psi 16 in this case. So my quantum state is a product state, but this quantum state only violates the terms that act on the boundary of this 2D lattice. So this quantum state is not really that energetic. It's only violating the length of the boundary, that's epsilon. So it's only violating epsilon fraction of terms. So whenever you have a situation where the boundary, like this boundary of the square, scales slower than the volume, which always happens in a low dimensional lattice, you cannot have this NLTS property. So NLTS property requires expansion, which means that the boundary should scale proportional to the volume. That can only happen in a very high dimensional or on expanding hypergraph. So that's what we need. The main point that we have, the main observation of this work is that expansion is also sufficient in some sense to get this result. So I'll try to get this point across in the next 8 minutes. Slightly running over time, but that's fine, I hope. So I'll explain why expansion implies this property of clustering, that the code words cluster together. And I'll do it with a classical example. The example of a famous code called the Sipser-Spielman code. In this code, you imagine a graph. You imagine a collection of vertices and edges connecting them. And these edges are in a manner that this graph, it's expanding. So I'll describe that intuitively in a moment. So this code has the following components. The graph has a collection of vertices and edges. This graph is a degree D graph. So let me write it down. It's here. It's degree D. And I imagine a small classical code, C0, which needs D bits to encode some small K0 bit, and the distance is delta naught. And the way this whole code is defined is that the bits live on the edges. So the bits are going to live on the edges, and the checks live on the vertices. So each check lives on vertices. So each check is defined by this code. And the requirement is that I want to assign bits to the edges in a manner that for every vertex, if I look around the edges or the bits for this vertex, those bits must be in the code space C0. Also here, they must be in the code space C0, this local code. So each check is local, so it satisfies our local property that we've been asking. And it turns out that it encodes lots and lots of code words. But the main point is that the distance between the code words or the Hamming distance of the smallest code word is very small, is very large. So the reason why distance is large is because, well, let's say you were trying to create a code word which was of low Hamming weight. So let's say I try to create a code word by putting a 1 here and trying to put zeros everywhere else. I cannot do that because I have to make sure that this local code is satisfied. So I need at least delta naught ones. So maybe let's say at least 2 ones here. But once another 1 appears, this check has to see more ones. So this check sees another 1 here, for example, and then this propagates. So a single 1 in this system propagates throughout the lattice. And that propagation increases the distance of the code. But you can ask, well, what about the approximate code words of this code? So what I pointed out here is that the exact code words of the code, they live far away from each other. The distance is large. But how about the approximate code words? That means the set of code words that are allowed to violate a few fraction of checks, well, in that case, the main claim that we have is that due to expansion of the graph, the approximate code words form clusters. That means they're sort of far from each other. And the way it happens is that, well, if two code words are approximate, then their sum is also an approximate code word. So the claim is that any approximate code word has high Hamming weight or a very low Hamming weight. And the way this works as follows is that, well, you're allowed to violate an epsilon fraction of code words. So you're allowed to, for example, put a 1 here and put a 0 everywhere else. That's totally fine. But you can only do that to some extent. So you can put another 1 here and 0 everywhere else. That's fine. But once you put enough ones, this propagation, and then once you're not allowed to violate beyond epsilon n fraction of code words, this propagation will happen again. So you'll start seeing this 1, 1, 1 all over the place. So again, the distance will increase. So either you stay small in terms of the Hamming distance, or you suddenly go far. So this clustering phenomenon that happens. And this phenomena, please ignore this point for now. This phenomena shows that this expansion of the graph leads to this clustering property. All right. So that's precisely what we show for quantum code words too. So we show that for the quantum code words discovered by these authors, if you look at the X part and the Z part, they also form this approximate clusters, as you see in this picture. They form these clusters. The real surprise is that the original code words may not lie in some of these clusters, but that's a technical remark. All right. So that's an intuition for how clustering follows from expansion. Let me talk about now in the last 2 slides. Let me talk about another point that I mentioned. Why am I looking for clustering? How does clustering imply that my state has high circuit depth? So the easiest way to do it, and probably the best way to do it, is via these 2 examples. Let's look at the state plus state. This is the plus state on all the qubits. Plus is 0 plus 1 over 2, our usual plus state. And let's look at another example, the cat state, which is all zeros plus all ones in superposition. Intuitively, we know that this state clearly requires a quantum circuit of depth 1 to prepare. I just start with all zeros and rotate 0 to plus by a Hadamard gate. In this example, I need much deeper circuit of probably much longer depth. But how do I really make this difference clear? The way to do it is to argue as follows, and that's sort of a standard thing that people have been doing in classical computer science, which has showed them in quantum world as well. The argument is that, well, let's say I measure these 2 states in the computational basis. In the first case, I would get a uniform distribution over n-bit strings, which I've denoted as a filled Hamming cube, space of n-bit strings. In this case, I would either get all zeros or all ones only. It turns out that, so the observation is that the distance between these 2 things in this picture of the cat state is very large. And there's a clustering happening here. Your distribution forms clusters far away. In this case, there's no clustering. It's all over the place, the distribution. So that leads to the main theorem, which is that given a state that can be prepared by a depth T quantum circuit, if you measure the quantum state in some basis, maybe you measure in the Z basis or X basis, it doesn't matter. If you are able to locate 2 sets S1 and S2, as here, this and this, which are far from each other, they have a distance D from each other, and they have good enough mass, like 1 over 10, then the depth of the circuit must be at least log D square over N. So the proof, I'll not go into the proof, but the key point is that in the case of uniform distribution, the D is actually root N. So D square over N is 1 and there's no lower bound. But once your distance within the sets is more than root N, you get a circuit lower bound. And root N is exactly where, if you know IID random variables or Gaussian distribution, you'll see that root N is very natural. So this is the standard deviation of Gaussian random variable IID distributions. So it's all connected. So that's the source of circuit. That's why we're looking for this clustering property. And finally, in the last slide, that pretty much brings you to the end of this talk. Of course, you can ask me questions about any of these, but some open questions. one very interesting open question is, can we prove this property not just for circuit depth, but also for other notions of simplicity, such as the stabilizer rank? It's another notion of simplicity that we have. Can we prove NLTS property for fermionic Hamiltonians, which was asked recently by Hastings and O'Donnell, which is probably the most easiest question in this list. Another question is that, is it true that any good quantum code, any quantum code which has high rate and high distance is NLTS? That's another question. Another question that I'm interested in is there a notion of robust order parameter in terms of topological order? And finally, the quantum PCB conjecture is wide open. So with that, thanks, and happy to take questions.
Thank you, Dr. Anurag. The talk is open for questions now. So you can unmute and ask questions.
Or clarifications, either.
Hello?
So this is a phenomenon of clustering. Either it was too clear or too unclear, which is both is not good.
Yeah, most of us are physics people. It takes a bit of time to appreciate this.
No, so please throw oranges and or rotten tomatoes. So what is wrong here? What do you feel reserved by as physicists? Let me go back to the previous.
Okay,
let me go back to the physics part. Yeah, sorry.
So here you are trying to find, like, you mean the depth of the code? You mean like how many gates you need it to?
Yes. So the goal is to argue that if you look at the Hamiltonian that comes from a quantum code, you want to show that any quantum state that has low energy with respect to the Hamiltonian, its depth as in the number of layers. So if you start with all zeros and apply layer by layer gates, then the number of layers you need to apply to prepare that low energy state is log n instead of log n that was asked in the condition.
How do you check whether the state prepared is low energy state or?
Oh, just measure the energy as in well, I mean, it's a theoretical question in the sense that there's no algorithmic aspect to it, but you can still ask that question. That's a valid question as to how do you really check the energy. So you just go ahead and measure it.
So for ground state, we know from the Hamiltonian, we find the eigenvalues of it, and we say, like, once we get the eigenvalues of it, the lowest one is for the state which is having this lowest eigenvalue. That state is a ground state, you are saying.
Oh, so that's a good point. So the thing is that the Hamiltonian that we construct always has ground energy 0. So we already know the ground energy is 0. If you want to, if someone gives me a state and I want to measure the energy, I just have to take one of the terms of the Hamiltonian. So if you see in this slide, the Hamiltonian is a sum of terms of x and z part. I just have to measure that term. So for example, I can measure the x stabilizer and z stabilizer and check whether I got plus or minus. And I measured it a couple of times. If I got lots of plus, then great. Then I'm close to the ground state. I have low energy.
Okay.
So I can do it physically. I mean, as physical as I can think of. I mean, maybe not so easy in practice because these stabilizers acting on lots of qubits. Like, I think in these codes of Mendeleev and Kalachev, these stabilizers act on millions of qubits. So, of course, it's not practical. It's all very theoretical. But
Okay.
In principle, you can do it.
So stabilizer, sorry, I don't know about it.
So stabilizers are the checks of a error correcting code. The code space, sorry, I should have spent some time on this. The quantum code is basically the collection of all quantum states phi, says that x to the a phi equals phi and z to the b phi equals phi. So these are the states that are the +1 eigenstates of the x and z and x to the a, but so sorry, what I mean by x to the a. So for example, if a is 11000, it's an n-bit string. X to the a will be poly x on the first qubit, poly x on the second qubit, and identity on third, fourth, and fifth qubit, and so on. So that's my poly x. A tells me where the x acts. That's an example. Similarly for z.
Okay.
So that's how stabilizer codes are defined. One writes down these stabilizers, and then the code space is the +1 eigenstate of all of them.
Okay, thanks.
So I don't think any more questions are there.
Mm-hmm.
So thank you,
It will
Dr.
take a
Anurag.
while. Yeah, it will take a while to get into our head because we are familiar with this kind of systems. So
No, that's totally fine. Yeah, I should have probably, yeah, this is where the talk is very unclear. So I should have probably spend more time on these concepts. But you know, if there are any questions, please shoot me an email. Very happy to answer that over email or something like that. Yeah. So, great.
So I have one more question.
Yes, please.
So you are saying no low energy trivial states means, so you are saying apart from like in the first slide or second slide you are showing the zero and ground state and a state above.
Mm-hmm.
In between there are no other states possible. That's what you mean? This no
Oh, no.
no energy.
So what I'm saying is that if you look at there'll be states all over the place. So if you look at the spectrum, there is ground state, there are states everywhere.
Yeah.
All the way here, everywhere. They're like, it's a whole space of, so this is the space of all, I'm just writing down the eigen values, but there are these quantum states all over the place. And the energies are all over the place as well. Sorry, what happened? Oops, I think for some reason my iPad, I'm not sure. Sorry. Yeah. Can you see the screen? No. Share again. The claim is that the question that we're trying to ask here is that any state that has energy in this range, for all the states, the quantum circuit that prepares the state from all zeros must have depth larger than constant, super constant. Or another way to think about it, all this is that if you're trying to do a adiabatic evolution, if you're more familiar with that notion, from a simple Hamiltonian to this quantum state, any adiabatic evolution will take a long time and cannot be done in a short time. That's another way to think about this thing. So in that sense, these are complex quantum states. That means there are quantum states here all over the place, but they're all complex in the sense that they require a lot of effort to prepare, like deep circuit or long time, something like that. So that's what the question asks.
Thank you, sir.
Thanks.
So thank you, Dr. Anurag, for this wonderful session.
Thank you so much. Thanks for the invitation. It was very nice meeting you.
Yeah, thank you. Thank you, Anurag. Yeah.
Thank you so much.
So with this, we have come to the end of today's session. Now I hand over the session to the organizers for any further announcement and close the session.